wabarakatuh. We're really sorry for the buses issue. It's out of our hands, so we're going to start. First of all, hello everyone. The Physics Club welcomes you to its second weekly meetings. In these meetings, we explore new concepts, discuss important articles, and get to learn from amazing people. Today's meeting is going to be a special one, not only because we're going to be talking about a special topic, which is quantum mechanics. More specifically, we're going to be talking about the second revolution, the second quantum revolution, but also because our speakers today is a special one. Before we start, I'm just going to give you a small background. He graduated, he got his bachelor's degree in physics and chemistry from Harvard University. Then he went on to receive his graduate degree in applied physics from Yale University. Currently, he is a physics professor at University of California, Berkeley. And he's also the director of the Quantum Nanotechnology Lab. Please, everyone, welcome with me, Professor Arfan.
Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. Can everyone hear me in the back with this microphone? Alhamdulillah. Let me thank by starting the hosts that are here, the professors in the department, the chair of our department, and the students for welcoming me back to this wonderful place. May Allah subhanahu wa ta'ala accept from you all your amal, all your hard work. Ameen. The topic of this evening is the second quantum revolution. So first I want to reassure any members of the political science department or any related department, there will be no revolution tonight of any flavor that's happening. We are only talking about a thought revolution in science. Alhamdulillah. You know, we heard this buzzword quantum computing. How many of you heard this term quantum computing? Alhamdulillah. So the press is doing a good job. It's out there. But it's more than quantum computing. That's what I want to talk about. If it was just computing, it would be a technology like anything else. And we have technological changes from your phone to your watches to so on and so forth. But really what we are talking about is applying a set of physical laws that we have never been able to apply in the same way. And that's a rather radical, different concept. That's a revolutionary concept. So that's what I want to take you on a journey with this evening. What is this concept? How did it come into being? How is it now applicable? What has changed? And what may change coming forward? At the very end, I also want to answer a few questions many students have asked. Well, how did you pick this path? How did you go in this direction? We save that a little bit towards the end, inshallah, if it's okay. Tamam? So that way to give a sense of how one sort of can enter this field, or rather to simply say that this field didn't exist when I started doing science. So I don't think one should always try to chase after the field, let the field chase after you. So we'll talk a little bit about that maybe towards the very end. So let me start by answering our host's question. He was here a second ago. He asked, well, what is the first quantum revolution? It's a great question. If you're going to talk about the second one, we should mention the first one. So let's talk about this. This really, to me, is the first quantum revolution. If you ever baked bread or did something else, you do it in an oven like this. And in fact, this is the oven of the potter. So you can see the clay pots that are there that are being heated. And this image represents to me the absolute and utter failure of classical physics at the start of the 20th century. Utter failure of classical physics. Because at that point, what did we have? We had the laws of Newton. Okay? We had the electromagnetism of Maxwell. Fantastic theory, right? To explain all light, all of these things. We had statistical mechanics of Boltzmann. So these are real pillars. You learn this in what? 101, 102, 201. Right, in your sequence. But they could not explain the light emission from clay. So you see, it's a very, very fundamental problem that Wedgwood of Wedgwood crystal knew in 1792 that all objects, when you heat them to the same temperature, will in fact, glow red. Doesn't matter what the material is. It only depends on the temperature. And classical physics utterly failed to explain this. Okay? So the model that you come up with in classical physics is that you think of the atoms as some electronic piece, some electrons, and they can jiggle around. They're oscillators. So these oscillators, it's in fact charged, so they will move around and they will emit light. Okay? And in the classical model, all vibrations equally emit light. So every possible way, every possible mode that you have will emit light. And if you add up all of these different ways, what will you get? You say it's infinity. Right? So in fact, this is called the ultraviolet catastrophe. Right? You add them all up, the energy density is infinite. Is that not an utter failure of classical physics? You try to figure out how much light is emitted from your jug, and you get infinity. Okay? So this is the problem Planck, of course, is trying to solve. And he says that light is not emitted at all possible combinations. It's only emitted in certain combinations. Right? And you learn this as packets or quanta and so on and so forth. The question is why? Why does it do this? Planck gives no answer. He just says, I don't know, it works. Really, he calculated, he said it seems to work. It seems to work really well. It explains the spectroscopy of the output perfectly. But there's another big failure that I want to tell you about. And out of these failures grows quantum mechanics. The other failure comes about, well, let's start thinking about the structure of this atom. So Planck is not very specific here. He says, you just quantize the energy. We don't know what's the structure of the atom, why is it quantized, so on and so forth. So you see, this model of the atom was very popular at that time. Because astrophysicists, you have polluted our thinking, right? Said, isn't it great you have all these planets, they go around the sun. Wouldn't it be great if the qadar of the creator is exactly the same down to the lowest sizes? So that's really what they're thinking. So if you look inside the atom, there should be something like the sun, like the nucleus, and you have all these electrons that go around just like planets. Utter failure again. Because if you think about this, the charge going around is basically oscillating. It's also emitting light. If you could take all of those orbits, how many possible combinations would you have of the light? It will be infinity again. And moreover, if you're emitting, you will lose energy and you will spiral into the center. How fast? Fractional of a second. So the atom is not stable in classical physics. Right? A tremendous problem. So it's no shock, building on the success of Bohr, that Bohr put out this paper, which is a beautiful paper. I encourage all students to read this. It's on the constitution of atoms and molecules. It's a very readable paper. Seriously, the original text from 1913. And Bohr says, number one, the physics of atoms is different than the physics of big objects. Why? No explanation. He just says small stuff is different. And it's different in such a way that you only have certain orbits. There's only certain stable positions. And you can see where this is coming from, right? Planck is saying that you have only certain emissions. He's saying you only have certain orbits. If you fix these orbits, of course, then you will not emit light, right, in these intermediate places. Why is this a big deal? This would have been just a perfectly reasonable explanation for things. But quantum mechanics comes with a very different set of philosophy. Not only does Bohr say that these are fixed, he also says the following, that in fact those are not the only places the electron is. So this is a bit strange now. You have these fixed orbits. You can ask yourself the question, how do you go from one orbit to the next orbit? At some point you have to be in between. Okay? So Bohr goes further and he says, you know what? Before you try to find the electron, before you try to measure it, it can be anywhere. And that's why I draw it as a cloud. Are there any chemists in the audience? One guy, Masoom, chemist. So the chemists, we teach this, right? Electrical clouds. That's what this idea is, right? The electron can be anywhere, but then you measure it, and you only find it in these fixed positions, right? If you measure it, you only find it here. So this starts to be a bit strange. Somehow we are saying that the reality of an object is more broad. It's not just the stable states. It can be anywhere. And you see where we will go with this ultimately. that if you build a bit, it can be more than 0 and 1 until you measure it. So you can see the seeds already starting to be sown here by Bohr. Okay. But it starts a tremendous discussion. Okay. Tremendous discussion between, let's say, these two gentlemen here. So Bohr says, he proposed that the quantum mechanics described where entities could be. Could be. The entities did not actually exist until someone went and looked for them. So they did not exist as particles until you try to measure it. The electron is not sitting in one of these orbits. It can be anywhere until you try to find it. And that's a very different concept. And Einstein absolutely would not have it. Einstein says, an electron was an electron, and just because someone wasn't looking at it, it was still there. Wherever there happened to be. I move this so you can see the bottom. So you see the very classical thought of Einstein, saying that it doesn't matter if you don't look at the electron, it's still going to be someplace. Right? And this is not what we observe in the world. If you don't look at a quantum system, it will be in some complicated state. But this was very difficult to swallow. So let me try to take you through some of these consequences. We just talked about position, right? Electrons have other properties. What other properties do electrons have? They have charge. And charge is where my theorists, scalar or vector property. All of us are theorists at this level. It's a scalar property, right? Plus or minus and a certain amount. Spin, on the other hand, is a vector quantity. So spin is, even if we're not familiar with it, it's some property of matter. In particular, it's a property of the electron. By the way, it's a bit strange. Sometimes we are fine accepting charge, but we have difficulty accepting spin as a property. But what's charge? Do we really know what is charge? No. In fact, how do you define charge? This is the interaction with the electric field. Right? So how do you define spin? The interaction with the magnetic field. Right? There's nothing specific. These are just labels for properties of matter. So you can have spin, and the electron has spin half, meaning that it only has two possibilities. You can either measure it up or down. Okay? The question is, what is up and what is down? Up and down are defined by your magnet. Right? Because in fact, the spin is going to interact with the magnetic field. If it points this way, then it will be up and down. Relative to that, if it points this way, this will be your up and down. So this is the basic property of matter. So let me take a spin, okay, which is, let's say, pointing up or down in the z direction, so to speak, and put it through a magnet. This was the famous experiment done by Stern and Gerlach, right, in 1922. Depending on the orientation relative to your north and south orientation of the magnet, the up species, say, may go here, the down may go here. Everybody learned this in some flavor of physics class? Okay. If not, you have learned it now. Okay. This is the Stern-Gerlach experiment. You put the spin through, and of course, just as if you had a charge, it would go in one direction or the other. Here, it's going in one direction or the other. So now let's start thinking about this idea of Bohr. Okay. Let's take an oven. Silver is very popular. So I take silver atoms and I heat them up a lot, and they come out of this box. And you can collimate them and so on and so forth, but let's imagine they come out one at a time. What is the spin that's coming out? Will it have a direction? What do you think? Sorry, louder? Until you measure it. You're a Bohr guy, you're not an Einstein guy. MashaAllah, very good. Until you measure it, you don't know the direction, right? That's what Bohr is saying. It can be in any random orientation. But then I measure it, okay, and that determines now the direction of the spin. Look at the logic and the philosophy. Your measurement is putting the reality of the z spin. Now, if you are Einstein, not a bad guy to be, by the way. If you are Einstein, what would be your explanation of this experiment, right? Because this is a physical experiment done by Stern and Gerlach in his native Germany. What would be that? Yeah. Accent. So he's saying that, in fact, you are going to only sub-select the ones that point up and down, because they were randomly created, right? And you will only measure the ones that are up or down. So this is an interesting point, Akhi. You cannot distinguish at this experiment between these two philosophies. Right? You cannot tell. From the experimentalist cannot tell whether it was your measurement that was imposing this or it was just a random selection. So this was the state. This is another critical point. This was the state of quantum mechanics for many decades, that even though the mathematics is different, there's no physical test to tell you whether this quantum behavior is different than classical behavior. Right? And at that point, it doesn't really matter what the theory is because the observable is the same. And this changed, as I'll show you in a moment, where we started to see predictions that are different of whether you believe Bohr or Einstein. So what if I change the direction? Same story. As we said, you will now put it along this axis, and our Einstein supporter there from the south says we're going to go either right or left this time. So the orientation of the magnet determines the spin direction according to Bohr. Okay, I'm going to skip this one for a second, and I want to go to this one. What if I now create a pair of spins? Okay. Just like when you play the game of billiards, you can imagine that there are two balls that are going right and left. This is conservation of momentum. Right? You had zero momentum before. They should always be anti-aligned after you hit them. So let's imagine I prepare an oven that always prepares anti-correlated spins. So it will prepare this green one and this gray one. Okay? And if I measure them, I break them apart. Right? I send one way, one the other way. Then you will always measure this anti-alignment. The one on the top is up, the one on the bottom is always down. Okay? Because I have created them with this property of being anti-correlated. If I measure the opposite, it will still be anti-correlated, but in the opposite way. Everybody okay with this? Okay. So now let's think about the following. If you put them in these different directions, right, they will now be aligned on the horizontal directions. And then you can start to ask the question, what if the distance between them gets very large? Okay, let's imagine I move them to actually galactic distances, to one side of the universe and the other side of the universe. What happens then? Okay. So you can imagine having a detector that changes the angle at which you measure. Okay, so I can take my magnet, I can rotate it. Okay. Can the orientation of this one affect the orientation of that one? The result. See, Einstein has a real problem with this, because if somehow they are still to be correlated, you will have to communicate this result faster than the speed of light. So then now you see the EPR paradox coming into view. If you really believe that this entanglement, so to speak here, is non-local, is a property of quantum mechanics, for Bohr there's no problem. Once you choose this detector, you also choose the output here. And that's just wild to Einstein, right? Completely impossible. So again, the question of can you tell the difference between these two methods? Actually, you can. Right? This was the genius of John Bell, right, in the 60s, where he calculated the correlations between the angle of this magnet and that magnet. Okay? So classically, you would say, well, randomly there is a probability that you will pick the right angles, and this thing is a linear function. That's this red little triangle shape here. As a function of angle, so you see if the two detectors are at zero angle, meaning they're relative to each other, they are aligned, you will always measure -1. Right? That's the anti-correlation that's there. If they will be 180 degrees apart, you will measure +1 because one magnet is up and one magnet is down. Okay? So on and so forth. But the quantum prediction is that if this entanglement is there, you will measure this curve because it's the amplitude of the wave function that matters. So this is the first time we're now seeing actually a curve which is different, depending on whether you believe this business of imparting the properties by measurement, so on and so forth. This experiment still has not been done. Extremely challenging. Because you would have to take an electron and move it some distance which is space-like separated, so some ridiculously large distance. So there's no way an electron, which our chemists will tell us, interact with everything, can be moved apart and kept non-interacting. So this experiment has never been done. But you can do it with a different object, which in fact does not interact with many, many things at all. What object can I use? Sorry? You can use a neutron, maybe, also possible. Maybe even easier for the experimentalist. Yes, say louder. Light. You can use photons. Photons don't interact very strongly at all, but they have, of course, a polarization. They can point one way or the other. So you can treat this polarization quantum mechanically and do the experiment. And it was done. First, actually, it was attempted at Berkeley itself in the 1970s. Okay. So there's a picture from the Lawrence Berkeley lab where they're actually doing this kind of Bell test measurement. But it was done most cleanly by this gentleman, Alain Aspect, in a really beautiful set of experiments in France, where he starts with a laser, he puts it through a crystal. So this crystal will do up conversion, down conversion, make the two billiard balls that come out. So you will have two daughter photons that are always anti-correlated. So that's how you create that particular aspect of it. And you send them, for him it was 12-meter distance, so light travels fast, so you don't have to go that far apart to test this in some reasonable way. And he put two polarizers. So the polarizers are like your magnets, right? You can pick the angle and measure this. And I will show you the original data. This is the original data from PRL 1982. You can see what is the shape of the curve. It's not a triangle. It's the sine wave. So this was a clear experiment that underneath the hood is this quantum behavior. And you can see it, and it's different from your classical prediction. Okay, so this was a tremendous experiment. 1982, a long time ago. Okay. So how does that turn into what the Europeans have called the quantum manifesto? This is something on the internet, you can read this. Again, this revolution manifesto kind of idea, no political entities have been involved. Although I think probably making the document is quite a very political exercise. Okay. So they are mapping out, let's say this was done in 2015-16 to 2035, what are the technologies that we have? Well, we can take these quantum properties and use them to make clocks, use them to make sensors, use them for communication, use them for simulation, and then I think it gets very fuzzy over here, where you try to use them in some kind of quantum internet and quantum computing and so on and so forth in some general fashion. So I actually want to take you a little bit along this journey to show you what are those technologies that sort of come into this and also where we stand. You know, how far are we now in this roadmap? Okay. So the first application I want to show you that immediately you can have secure communication. Okay, so let's talk about the communication problem. Okay. Anyone study Greek history? The Yunan? Real fan of this history? The Yunani, they love to go to war, as you know, with the Spartans and so on and so forth. Okay, so this is how they communicated. This is called the cityle. So if you want to send a secret message from one boat to another boat, or something like this, you would take a stick, a cylinder, that's what the cityle is, and you would wrap your message around the cylinder, okay? And you would space out the letters so that when you wrap it around the cylinder of the right diameter, you can read the message. That was cryptography in the time of ancient Greece. Okay? Now, if you wanted to break the code, what do you need to do? Just figure out the size of the cylinder. You get the cylinder and it's all over, right? But interesting, you have a physical key. It's not different now. I will tell you also about quantum key distribution, right? It's still a physical key. Here, the key is this piece of wood that's there. By the way, in World War II, you did the same. That's the Enigma machine. Right? So when you send signals that are there, the rollers, on the back of the Enigma machine, you have to set their distance so that when the message comes, you get the right sequence. It's the same stuff, right? But now you're using telegraph signals and little rollers and little, not wooden sticks. Okay? So how does that change in the quantum case? Okay. At the moment, we send messages, let's say between you and your bank or something like this, and you send them through a classical channel. Okay, so you put it through the internet, so on and so forth. The message is always open. It's not hidden. There's nothing secret about the message. But it's encoded in such a way that it's not obvious to make out what it means. For example, if you try to read this, you may have a little bit of a hard time reading this. However, I can tell you that for this lecture, I have used the key KFUPM for obvious reasons. So if you take out this key, you should be able to read a message. Can you read the message? Iowa? Good. Okay. So this is an example of classical key distribution that's there. So the critical part is the key, the message is on a classical channel, but you have to make sure that somehow this key is not broken, because if you know the key, then you can decode the message. In modern communication, this is done by using numbers which are difficult to factor into their primes. Okay? So now you can see the application that's coming in of quantum computing. The key is made up in such a way, as I'll show you, that multiplying two prime numbers, very easy, sahal jiddan. To factor them, saab jiddan, very hard. Okay, so that asymmetry is what's used for communication. So public key distribution, both parties exchange prime numbers and multiply them to get the key. So that's what you're doing. So how would you do this in the quantum case? So you see, you take those two little particles that I showed you, you split them, you send one, that's the key. Okay? And this is actually the protocol called Bennett and Brassard 84, the very first one, Baby 84 in 1984, that you split this entangled pair, you distribute them, both parties measure randomly, and then you communicate with each other the results. And you see, if you measured the wrong axis, quantum mechanically, you will get a different answer. Right? So you will know when you have the wrong key, and you throw away those entries. So this is how quantum key distribution works. Again, a physical exchange of the photon. You measure them, and you're using these quantum properties to make sure that you're measuring the right key. Does that make sense? Okay. Now, what's also interesting, I asked you what happens, how do you break the Greek code? You steal the little rod. How do you break this code? How do you break the classical code? Well, you figure out, right? Somebody goes in and hacks, an unknown country will go and hack the key. This one, you cannot actually do it. Because if you measure the photon, right, before it reaches the other party, you will disturb it. And the other party will know that somebody measured it. See that? Because what? Bohr said, when you measure it, you give it its spin direction. So if you measure it along the way here, you mess it up. So not only is it secure, you also know when someone measures it. Okay. So this is a very useful way. You can see communication is immediately possible with this, and it's being done. The Swiss did this a long time ago to secure their elections. Not in the US, obviously, right? But the Swiss did this to make sure that there was no tampering. And in fact, there are networks of fibers all over the place. So this is in the US, there's a network now in the middle of the country. And the Chinese have really taken this to another level, right? So here are all the Chinese cities, for example, with 1,200, at least more kilometers of communication happening here. And in particular, they're trying to use a satellite where you send photons into the air, right? Rather than through a fiber to extend the length of this QKD, quantum key distribution, as it's called. So anyway, this technology is making its way into some very advanced state. You can see here. Okay. Yes?
How to make sure that the photon will not be disturbed by anything else in the medium that transfers the photon?
Yeah, that's a great point, right? So in fact, if there is some noise or decoherence in the channel, that will limit the distance over which you can have this communication. So in an optical fiber, you are limited to about 100 kilometers. Okay? Because after 100 kilometers, the signal decays because of loss or this interaction. So the goal with the satellite, of course, is to have much longer free space communication. But there's a little subtlety here, which I think the Chinese are not making very obviously known, is that the state that you really need to send for a physicist is a Fock state, right? It's not a coherent state. And that nobody has any clue how to do. So these are all attenuated coherent states. And the question is, what is the security of these states versus pure Fock states or number states? This is still debated at the moment. Did I get the question? Okay. So then this is a 1-2 qubit kind of operation, right? One photon, one entangled pair, a few entangled pairs. For computation simulation, we're talking about many, many more entities, right? And why is that more powerful? Think about this. If each one of these points was this kind of quantum object, this quantum spin, how many numbers do you need to describe an array of this? Okay. The first one is just 2, up and down. Then I entangle the next one, and you see they're correlated. So it doesn't grow linearly. The next one also entangled, so it grows as 2 to the n. It doesn't grow as n times 2, right? And that's a big difference for an entangled subspace of even 100 elements. Okay? So these units, they cannot be described as an individual piece. This is the EPR question. When you measure one, you have already learned something about the other one, because they're correlated. So in fact, to fully describe, as we said perhaps the other day as well, 300 qubits would require more particles than the particles in the numbers in the universe. You would need more numbers than that, right? That's 2 to 300. So the key, again, you see, going back to Bohr, the actual space that this electron or this arrangement of electron lives in is very large. You just cannot see it at any given time. It's there. but you have to learn how to manipulate it. And that's what it means to write a quantum algorithm. Something that will not project the state, will not relax the system, but allows you, in fact, to use this very large computational space. Okay? So this is the challenge of the algorithm designer. Okay. By the way, we already use quantum systems, right, in large arrays. Many of you have studied NMR, MRI, so on and so forth. In fact, you are actually polarizing all these spins. You're a nuclear guy, like this, right? So you polarize all of these things. This is a perfectly fine quantum system. The only challenge is in NMR, we are not accessing them one at a time, one side at a time. You're looking at the average behavior, let's say, of an ensemble. So really, quantum computing is single spin NMR. You want to actually access each one of these spins and couple them together, okay, and uncouple them as needed. You get a very nice image here, even from the average behavior, right, of the spins. You can imagine the sensitivity you would have if each one of these are truly quantum and accessible. So you see, we talked about communication. I'm bringing in sensing for you now, right? Each one of these quantum objects is very sensitive to any sources of decoherence. You can use that as a sensor. Okay. Again, an application which requires only a few qubits. Okay. But in the final part, let me talk about computation. Does anyone recognize what this picture is? Yes? Transistor. Old transistor, right? Very first Bell Labs kind of device. Huge tabletop device. This is, I actually had to remove the water from my iPhone, so I took it apart and decided to take a picture while I did it. It was quite some work. So that's what's on the top, right? And in particular, the transistors in that one or in the Titan supercomputer on the bottom, what you have really done is simply change the scale of your transistors. You have not changed the logic. They are still 0, 1. They're just a very small size, and you can pack a lot of them. So what I want to start here is to say that quantum is not the next limit of this, where you go even smaller. That's not what we're talking about. In fact, it's going to change the entire structure of how information is stored. And it's a very different concept. So you see the classical bit here, for me, is just a voltage. Sorry for all the electrical engineers that are here. Basically, you have 0 or 1, 0 volts or some finite voltage. Quantum is not that. Quantum is saying that the bit can be any combination of 0 or 1. It can be a superposition, right, to access this large space. So that's totally different. Here, you write 0 or 1 and you read 0 or 1. Right? You have one or the other. Quantum, you write 0 and 1. Right? So this is an interesting concept. How do you write 0 and 1? As long as you don't read it, it's fine. Okay? But you read what? 0 or 1. Because your spin can only be found in these two states, but it can live in any other combination. So you see that? You can be in any combination, but the readout step is always returns this classical behavior at the end. Thank you. Okay. So let me show this for a very simple electrical engineering device. Okay. Let's imagine you have n bits. So you have a register. It can be up or down, up or down, up or down, up or down. The first row of the register, for example, can be simply zeros. 0, 0, 0, 0, 0. Then you flip one of them. It's almost like a child's toy, right? You have them on some kind of abacus. You flip one. Then the last one becomes 1. Then you can flip maybe the one next to it, okay, so on and so forth, till you get to the bottom where you flip all of them. Okay. How many combinations do you have? 2 to the n, right? Okay. But how many states can this arrangement occupy at one time classically? 1. I see it there, right? You flip it, and that's it. But you see, quantum mechanically, you can write all of them together in this entangled wave function. So you see the entire register is one wave function, which if you measure it, would only give you one output. So the question is, how do you actually use this wave function? So I'm saying the same thing a few different ways, right, to resonate with you.
Excuse me, Doctor. Student will have the information. This one-wave equation will have all of the information?
Sure, because for example, you can write a state of up plus down, right, in your spin system. Spin sideways is spin up plus spin down. This is a system that has not 2 configurations, it has 2 to the n. So it can be this eigenstate plus that eigenstate plus that eigenstate plus that eigenstate all together. So slowly I'm taking away from this electronic structure, right, to something which is more physical. Okay. What is it good for? Let's imagine I have this state. It's good for physics experiments for sure, but what practical use can it have? So this is the thing I think that got many of us excited, as I mentioned. Peter Shor came up with this idea that if you take two prime numbers and you multiply them, this operation is very easy, classically microseconds, if not faster. The reverse operation will take you more than the age of the universe to do. Because classical computers are not good at that particular logical step. Okay? So in a quantum machine, you could probably do that in hours. So you see, everyone starts to get worried now because all the security, the codes, the RSA encryption, all of this can be broken, maybe, right, if you have a quantum machine. In all truthfulness, many things have happened over the last 20 years. There are now codes which are resilient to this. So we don't use prime numbers all the time anyway. So that's just an important point to note. We may be solving a problem that's no longer a problem. Okay, but that's how it started in the beginning. What about searching a database? This was another critical algorithm. So you can take, let's say, a deck of cards, and you make a superposition of all of them, and you want to say where is the ace or the queen or what have you. So again, what you need to do is measure the wave function, and when you project it, you will find it. So you see, quantum again can encode all of these possibilities. Okay. That is, in fact, the long-term application. You would need a lot of qubits, a lot of control to implement those algorithms. So near term, you hear this term quantum simulation. So what Feynman suggested many years ago was that let's imagine you take a bunch of atoms, okay, and you try to solve their electronic structure. You cannot do it classically. It's very complicated. However, the atom knows the answer. Right? So if you take the nuclei, you put them together, it will find the ground state. So if I had a machine where I can just control the couplings, I will have a hardware simulator. So you see, you can let quantum mechanics do the computation and just read out the answer. Okay. So this was Feynman's idea of simulation. You engineer the connectivity, you let the system evolve quantum mechanically, that's the hard part that you can't calculate, and just read out the answer at the end. So let me show you one problem where this is extremely interesting and useful, perhaps. This is a plot of the number of atoms that you can calculate in a chemistry problem using modern computers. The blue line at the very bottom, sadly, is the exact solution of the Schrodinger equation. It's less than 10, right? And it's scaling very slowly. So there's very little hope of solving complicated problems. All the other methods are approximation. Okay? So even if you had most powerful supercomputers with large memories, you would still be limited to, let's say, less than 100 qubits. Okay. If you're a real math guy, you can use DMRG, renormalization group methods, etc., and try to do better. You only do slightly better. Okay. Because every quantum element that you add is exponentially more complicated than the previous configuration. So this doesn't matter what your memory is. You will never be able to catch up with that scaling. Why is this so important? So I want to point out this particular chemical reaction. This is the method by which we commercially produce ammonia. Okay, this is the Haber process. So you take nitrogen and hydrogen and you put them together at very high pressure, very high temperature. Okay? So I want to note that this currently consumes 1 to 2% of all the energy on Earth. It's just this reaction. It's amazing, isn't it? Because this is what you need to produce fertilizer. This is what you need to produce all industrial reagents that are there. So it's extremely important. This is what feeds the world. Without this, you cannot grow plants. Okay. Also funny, at the same time, that naturally bacteria do this at 25 degrees in 1 atmosphere. So if you go into the roots of plants, this is happening at ambient conditions. But they make use of a catalyst, shown here, an iron cobalt catalyst, and we have no idea, iron molybdenum catalyst, we have no idea what the structure of this catalyst is. We can't even solve the 10 atoms that I showed you on the Schrodinger equation, forget the catalyst. So the claim is that classically there is no path to understand this catalyst. Quantum mechanically, even with 150, 200 qubits, you may actually be able to model the dynamics of this catalyst. So you see, that would be a very dramatic result for energy production and world production with very near-term applications. Okay. There are other things like this. You can think about drug delivery. How can drugs bind to certain sites? What are the dynamics of such sites? You can have improved artificial photosynthesis. Can we generate light and light harvesting in a better way? So all of these applications coming from the quantum dynamics of such systems. Okay. So this is hard to read, but I wanted to put this source out there. There are many reviews on this subject, and if you look at the next decade of quantum computing by BCG, the Boston Consulting Group, they have a very nice article. It's very readable without a lot of math and what have you. And these are the list of applications they show. So there's machine learning, artificial intelligence, security, scheduling problems, aerospace industry, catalysts, trading, portfolios, optimization. And you can see the list of companies that are there, including the Dubai Electric and Water Authority. NASA. BP is there. So your neighbors are also investing in quantum computing. Okay, so on and so forth. So how far away is it? Right? Just ahead. What does it mean? Here are the systems in which you will see quantum mechanics, everything. Right? Because you remember, in the beginning we said that this quantum behavior starts with electrons, but it's not restricted to that. Everything is quantum mechanical. So you can trap ions, use molecules, use quantum dots, you can use circuits. Okay. I use circuits, so in fact these are produced in semiconductor style fabrication. Okay. These are some tunnel junctions, for example, that go in there, very small sub-micron devices that are there. Now you cool them down. This is a picture of a dry dilution refrigerator. I sort of, with Photoshop, there's no hole in there, otherwise it would not work. So with Photoshop, I took out the outside part so you can see what's inside, all the electronics that are there. Okay. This is the chip. This is a more recent chip. The one on the cover was a little bit older. But this is one that's actually being measured now. It's version 5. Okay. And in fact, you can see all the qubits that are there and the coupling and what have you. This is an 8-qubit chip. Each one of the black boxes would be a qubit in this case. Okay. How do you measure them? The signals are tiny. 1 microwave photon. So we build our own amplifiers to measure these microwave signals. Here's the picture of an amplifier for 1 qubit. Here's a picture of an amplifier with 2,000 Josephson junctions, which we can use to multiplex all our output signals. What do you see? I wanted to show you this picture, because after all, we talked about spin. So we learn in the textbook that if you make a superposition in purple and you measure it, you will get either blue or red. How does it actually get there? So this is an artist's conception of those paths which are there. These amplifiers are so good that in fact you can track the signal that comes out and statistically come up with a model of how to update your state. Okay? So I want to show you the movie. This is what happens when you use that statistical updating. You start with a spin in purple, which is a superposition of up and down, and you can see in fact what we believe to be the dynamics as it goes from red to blue. And you can see once it hits an eigenstate, it stops. And you are saying, you already showed me this movie the other day, so I'll show you more. Okay? What if you measure many of them? So here's 4. So you see, in quantum mechanics, it's not obvious what your measurement will result in. This is how you get the 50-50 distribution. Sometimes it will go up, sometimes it will go down. So here I'm showing you trajectories, 2 of them that are tending towards the North Pole, 2 that are tending towards the South Pole. Okay. And again, the statistics folks here will say, we picked only 4. How do you know that always 2 will go up and always 2 will go down? You're right. So we measured on the cover of Nature, this is 1 million of them. And then you can study their statistics and understand what's the average dynamics of a quantum system. You can think about quantum GPS. What's the most likely path to go? So all of these concepts are now defined for us. Okay. And finally, can we actually do a computation? Yes, this is in fact the algorithmic sequence that we run for figuring out the energy structure of molecules. So you start off, I remember there was a question in the seminar the other day, so I put this back. If you have the hydrogen atom, the electronic structure problem, you have 2 electrons and 3 degrees of freedom, so you need 6 parameters to fill. The 6 parameters are here. I have 2 qubits. Each qubit has, I can drive it, it has an amplitude and a phase. And then I have the interaction between 2 qubits, and that interaction has an amplitude and a phase. So that gives me 6 parameters to play with. So I prepare the 2-qubit system in a certain state, I let it evolve, and then I actually measure to figure out what its configuration is and calculate the energy. And I keep doing this till I find the minimum energy by changing those parameters. And if I do this, I can actually generate the energy structure of hydrogen. So you see, with the quantum machine, we are now starting to actually compute these spectra. For hydrogen, not so impressive, it's only 2. However, as I said, beyond 30, there's no classical machine that can do it. So we're not so far away from that. And I showed you a chip already running with 8. And of course, I'm showing you the previous generation. What's actually running in the lab is perhaps even a few generations beyond that. Okay, so we're getting there. So finally, what I want to end with is we have started a new project sort of on Berkeley soil, which is the equivalent of a particle accelerator, but for quantum computers. We would like to build a very large machine that has many qubits and that allows us to put in different technologies, different types of qubits, different processors, so on and so forth, different software stacks, so that we can make this process go a lot faster. So this is called the Advanced Quantum Testbed. So this was what was referenced in the title. So here's a picture of the refrigerator that's likely going to go in to give you a scale bar. Khalil Harabi is saying all pictures look the same. This is right. This is 1 meter in diameter for the cold space. That's pretty big compared to old fridges, which were this big in the entire volume. So this is 1 meter by 1 meter depth. Okay. This is now the more realistic version of processor that we're building with multiple chips on different layers to give you more qubits. I only showed you the bottom layer, right? That had 8 that were there. To control all of this, we have our own custom electronics, FPGAs that are built in-house and used to control the system, so on and so forth. So it's a whole endeavor to scale this up. So it brings together national labs, industry, and academia. Okay? And I want to stop with this slide to say that, look, specialized quantum computers are here. This is quite exciting. Applications in basic science, I walked you through a few of them there, in the chemical domain, and so on and so forth. Error correction is something we have not talked about. You asked a good question. How do you know that your system doesn't get perturbed? It does get perturbed. So how to preserve this information is a very big open challenge. And of course, what about different theories for complex systems? Can we use machine learning to understand quantum systems? This is an interesting concept. And finally, what is the advantage? At the end of the day, will your quantum machine do better than your classical one? Not clear yet. This is something we have to study. So I want to stop here and take your questions. Thank you.
Any questions?
You have a question? Yeah. What's the question? Oh, he has a real question, but okay. I was implanting the question by measurement. Yeah.
No, I was just wondering, in terms of a computing perspective, how would this change the way we design algorithms, for example,
That's right.
So the idea is that you will actually have to design algorithms that are compatible with that logic. So totally different than what you do now. What's also interesting to point out is that quantum computers do well those things that classical computers do not, and vice versa. For example, if you try to add on your quantum computer, it's absolutely horrible. It's very difficult for it to do. So you have to design all the algorithms from the beginning. Faddal Sidi.
What you said about we have quantum computers, everything will be happy. So it will be design system to have a quantum computer.
Yes, you are representing the US viewpoint of why it's great to have a quantum computer so you do not get hacked. Excellent. I fully support this, to support funding for all of these things. I fully support it.
US has this quantum computer.
Then KFUPM should also invest in it so we all have it. That's how it works, right? Then you'll get a lot of funding to do this. And neither of us will have either this computer because it will look very different in 10 years. But we'll have a lot of good funding. Yeah.
Professor Arfan, I think you forgot to tell them how you got drifted into it.
I'm going to get there. I was going to see if somebody asked about it.
Yeah, this field is so much complex, and you started, as you mentioned in the beginning, started doing these things when even this field was in its first stages. So how did you get into this field?
It's perfect. Before I answer that one, because that's sort of almost the terminal note on this, there was another question up there, right? Can we take that one first? Yes.
I was going to ask, how long do you think this technology is going to be available at the consumer level?
That's a great question. So I think we have no idea what the real applications for this are and what the appropriate technology is to realize them. So if you look at classical computing, before the integrated circuit, before the proper silicon technology to do this, we didn't have computers everywhere. They were solving very specialized problems. So we're in this kind of stage. So I think it may be very soon, it may be very far down the road. We still have to find the right applications. So now let me get back to this question. Please.
This whole thing, it's going to have dramatic effects on the way human beings think.
Yes.
I think eventually. And I mean,
Yes.
I don't know if I'm right, but I mean, quantum mechanics, like psychoanalysis, is something that came about in the 20th century as kind of an opposition to rationalism.
Yes.
This introduces some kind of new rationalism, which
Yes.
is based on quantum mechanics. Because if you go along this way, And eventually, what type of course are you going to teach in a physics class?
That's absolutely right. So in fact, we already have these different philosophical pathways. So cubism is out there already. As cubism, quantum Bayesianism, to think about, is there an absolute reality? Is your view imposing reality on what you see? So already, yes, it's changing. The usual Jungian, Freudian ways are sort of going away.
What are qubits?
So a qubit is any physical system for which you can isolate two quantum states. It's not necessarily a two-level system. It can be a five-level system, but you can isolate two states.
Most I have two electrons, one down, one up. How do I make more than qubit? If I have only one qubit, it will have two states.
So you're right. So you can take one electron, right, or two electrons to form a pair that are there. So folks that work with, particles, they trap them using laser beams and optical tweezers. So you build a potential which looks like a corrugated lattice, and you put one electron or one ion in each one. And that's how you build up a system of many electrons or ions. So one at a time. And that's why it's very hard. There was a question?
So, quantum computing, can we say it's like an accelerator for computations, similar to graphics card or FPGAs?
I think not, right? Because if you have a GPU or some other NVIDIA base, you're still using x86 or RISC instructions, and you're parallelizing the process. Here, what you're doing is you're changing the complexity class of the problem. So it's not only that it's just some addition to your classical hardware, it's going to start, just like the algorithm question was, it's going to start from start to finish, right, to have its full computation. The only caveat that's there is that some of these algorithms now are hybrid. You may not want to do all the steps quantum mechanically. There may be only one step in the algorithm that's hard. So in that sense, it may be a coprocessor rather than an accelerator, right? It will not make your classical algorithm go faster. You're going to break it up into pieces and do some of them quantum.
You said that quantum mechanics has a mini configuration. So if I send a message to someone else from the cloud or anything else, how can I determine the configuration if any configuration could be found after the measurement?
Right.
What's the configuration?
Right, so what happens is I keep sending the message, and you measure it, right? Every once in a while, we will measure in the same direction. And when you do that, you get a unique answer, not a distribution. So that's why we keep talking to each other and say, did you get this answer? Every time you say yes, we keep that key. It means nothing bad happened along the way. So it's statistical. You have to send the key many, many times, and only a certain number of keys will be kept. There is. You can go ahead and try to generate a very specific state, so that's deterministic. You can do more complicated things than simply try to measure it, right? For example, you can encode in many qubits and try to measure the parity. So there are other ways rather than just measuring one.
We can say that the quantum computers are really affecting cryptography field. So is there any papers or research to overcome this problem?
Say that last part once more. We can say quantum computers are? The control.
Encryption.
Quantum computers are really affecting the cryptography.
Yes.
So is there any research or papers to overcome this problem? Any suggestion to resolve this issue?
Yes, there's many papers on this. And in fact, you can look at the title of Post-Quantum Cryptography. Just search for this, and you will see what is the latest status of the quantum algorithms that are there, and also the classical algorithms that are not prone to this. So both things are happening at the same time. Your superposition, so whichever way you want to collapse it.
So basically, you said that you send an electron between two magnets, and then, but how do you know it's pointing up or down?
You send an electron, then you measure it on the screen, let's say, right? And in fact, you will have a detector which will tell you whether the spin is up or down. So you'll have to have this is an important question, how do you measure your quantum system? So I need something which is sensitive to the orientation of the spin.
But what does it mean to have the state being up or have the state being down?
Remember, the spin property is only defined by a magnetic field. So if I put a magnetic field afterwards, if it moves in a certain direction, that means spin up. Just like if I put an electric field, if it's going towards the plus part of the electric field, it's plus charge. Or, minus charge in this case, right? Or opposite. So remember, properties are only defined by physical things that you observe.
A little while back, I saw IBM claim that they had the first quantum computer.
Yes.
Is this correct?
This is correct. They claimed that they had the first quantum computer. Absolutely correct. Malish. بالضبط. The claim is absolutely correct. You can see we're some distance away.
Yes, I was just wondering, in terms of architecture, how does a quantum computer differ from the classical computer?
Okay. So again, classical computers have a cache, have a memory, have some other output. So they are the quantum analogs of these things. And you may use different technology for that. So certain spins, nuclear spins, are great because they don't decohere. So that's a memory, but it's not a good processor. So you will have nominally the same parts, but they have very different functionality and very different materials. Okay.
The theory seems to be complicated to understand on its own. So what would you recommend are the prerequisite building blocks to understand the theory? You presented some statisticians, some physicists, some chemists.
Right.
Which is some subject we need to understand to grasp on the quantum theory?
I think the amount of quantum mechanics you need to actually understand the basic of quantum computing is very little. Right? You superposition, projection, that basically gets you there. Then how to build an algorithm is a totally different business. Right? It still builds on those same principles, but it's some very complicated concatenation. But I think start with basic quantum mechanics, you'll be in good shape. Yes?
By measurement, we can know that by measurement the material can know that we see it. So can we assume that the material that we measure that is a biological entity instead that is not a biological entity?
Can you say it once more?
Can we assume that what we measure is a biological entity, like a living organism instead of a material?
I don't know if you can tell the difference with quantum mechanics between the two, because after all, we're made of the same stuff as this thing. You pick. This gentleman here. We picked the wrong one, but okay.
My question is, how portable would quantum computers be in the future? Would they be embedded systems? Would they exist in embedded systems or not?
So at the moment, again, not having the technology that allows you to have quantum behavior in your pocket, right? We don't know how portable they would be. All of the things I talked about would be more of a general thing that you access through the cloud, say, right? So you would use it for very specialized computations, which is no different than classical HPC or supercomputers. Right? We don't own the big Titan machine. You just go online and use it. Okay.
This is going to be a shot in the dark. It's not really going to be a good question, but
it's a great question. I love it.
In what way is a measurement sort of defined? Because when you say if it's measured, then it's real. Is it related to consciousness, or is it just...
That's a great question. Don't shy away from that question. It's a great question. So there is the whole question of measurement in this context is a very mathematical term, right? So I multiply by two things and I get some information out of the system, right? So there's a very precise way to do that. But again, in the question that you were asking, if you start thinking about reality only coming about because there's some conscious measurement that's happening, this is a great question. We don't have a good answer for this, right? How does consciousness relate to this measurement? That's for you to study, Buzz. Yes. Yes, so there are gate sets that are very specific to quantum. But so in the classical way, you have AND, XOR, so on and so forth, Hubbard, so on and so forth. Here we have the C naught, controlled naught, right? And then in notations on each ones and so on and so forth. And they're Hadamard gates. So there's a whole set of gates which are parallel for that.
I have a question, two questions. The first one is about how confident we are about some of the experimental details, the experiment we perform. So, for example, the Stern-Gerlich experiment, in order to resolve the two states, we have to have a gradient in the magnetic field in the opposite direction. But that has to be accompanied by a gradient in another direction, along X or along Y.
No, not always. Only in the Stern-Gerlich experiment, but in modern versions we can get around that. So we're pretty confident about that. But that was a good point.
Yeah, the second question is about, you said in the seminar that quantum theory has not been tested at the level of complexity.
Yes.
And we may need another theory. And can you elaborate more on
Yes,
that?
for sure. For sure, I want to link.
Necessary.
Good, I want to link that with the last one. Is there any other? Yes.
Like in communication, we have different relations in mind that just one. Yes. How can we relate
The same in quantum, right? So for example, you will have different states and you encode them in different wave functions, so on and so forth. It will be a similar concept, but different physical states. So it's the same.
Last question.
How can quantum computers will help us in cosmology or in the universe, studying the universe or studying the theory of gravity?
So there are multiple ways to do that. One, you can try to simulate the dynamics in these many-body systems, like in black holes or in cosmological systems using your quantum system. We do that. So I didn't show that, but we do that. The other thing is to understand theories of gravity that really rely on this correspondence between ADS and CFT, right? Anti-de Sitter space and conformal field theories. So they're a way to understand mapping of this complexity in the field theory way to, in fact, quantum information science and also condensed matter physics. So at basic theory level and also at simulation level. Good. So now let me get back to your question, your desire, and your reminder all together. I made this comment, I said, don't chase after a field, let a field chase after you, right? Because the point is that science develops, and today we're doing something, tomorrow we're going to do something else. The most important and critical aspect is don't settle for mediocrity. This is not in Nardin, this is not anywhere to be had, right? So my own journey was studying things that are very different, but really trying my best to do that. Right? So in fact, if you looked at my choice of graduate school, it was a very interesting one. When I went to Yale, there was no quantum stuff at Yale. In fact, it was not actually a very popular place to do physics. I had gotten into many graduate schools, alhamdulillah, MIT and so on and so forth, and Caltech. But my father was very ill at that time, so Yale was only 90 miles from where we live. So I said, I will go to Yale. And subhanAllah, what happens? The kings of this field afterwards actually came to Yale because they wanted to relocate there from France. So it's very strange. I didn't actually have to go anywhere for a postdoc. I stayed in the same place for PhD and postdoc, which is very rare. But that's because my postdoc advisor moved. Right? And now, of course, Yale is a very popular place, right? One of the places to do this. So the point is, make sure that you target, right, and doing something which is very good and at the highest level of quality that you can. Pick a field where you actually learn skills and test your skills. Don't pick the easy way out. Right? There are many easy ways out in life and many things. Don't do that because you're cheating yourself for doing that. And when you do that, it'll be fine. And the technology will change. And I'm sure I will not be doing this in 10 years. Right? The skills are the same. I was not doing this 10 years ago. I'm sure I will not be doing it in 10 years. But the point is, it's a journey. You go from one spot to the other spot to the other spot. So just make sure that you have the right baggage for the journey. Right? Hassan al-Basri had said that if you go into the desert and your amal do not have ikhlas, they don't have sincerity, you're carrying the mashq for your water, but you fill it with sand and not with water. But don't do that. You're doing the hard work, but you're not getting the benefit, right, of doing that. Okay. So I think that's the most important thing that you want to do in terms of the path and the choice, right, of the field and so on and so forth. And what will be different after this? Well, we're going to inspire you to look at this because this theory, like all theories of physics, is subject to some violations, which we have not found yet. So the quantum mechanics of this circuit is the same as the quantum mechanics of the atom. It's just one particle, Hamiltonian. Can you write it for a Hamiltonian with 1,000 particles that interact and are independent? Don't know. By the way, to elaborate more on this, you can never get classical behavior from quantum mechanics. It's a linear theory. So it doesn't matter how big a system you make in quantum mechanics, the Schrodinger equation is the same, it's linear. So in high energy physics it's different. You can go to high speeds or slow speeds and you will see relativity versus not. You will not get classical physics ever in quantum mechanics. So that's a little bit of a problem, right? Can you actually build the universe out of these quantum particles and see the behavior that we have? Likely not. But that's the challenge for all of the young folks here, right? Think big, think differently, right? And don't get stuck on what is the one-year application or something or is exciting. It's great, to go into a field that's good, but think beyond that. So with that, I think I stop.